The last reaction that we are going to do in section 23.5 is called the Gabriel synthesis. Gabriel synthesis uses a really specific reagent to do an SN2 reaction to convert an alkyl halide into an amine. So here's our reagent. We're going to call it our Gabriel reagent. It's a 4-step process. Hydroxide, which gets that reagent ready for the reaction, followed by an alkyl halide, where the SN2 takes place, followed by H3O+, and then OH-. And that, the H3O+ followed by OH- is not redundant. Like in a couple of the other reactions we've looked at, you could just, instead of doing H3O+ followed by OH-, you could just do water, but that's not the case for this particular reaction. So this reaction generates an amine. On the amine, the R group from the alkyl halide is the R group of the amine, and the nitrogen obviously is coming from the Gabriel reagent. It is possible, instead of step 3 and 4, as they're written here, it is possible to just use NH2, NH2. Well, typically, strong acids and strong bases are easy to get your hands on in the lab, so that step 3, step 4 is usually an easier way to do the reaction. So this, just written out as steps like this reaction looks pretty magical. So let's look at the mechanism with a specific example. And for this reaction, I'm going to use a chiral alkyl halide, just so that we can practice SN2 inversion of stereochemistry, because that is definitely something that you don't want to forget. So first thing that happens is just simply deprotonation of the nitrogen. And a lot of times this particular first step is just, this is what's written as step 1 on the arrow. So a lot of times on the left-hand side of the reaction, you just see the alkyl halide, and you don't really see this deprotonation part drawn out. And once this guy gets deprotonated and it's ready to react, we're going to bring in an alkyl halide. Let's bring in, like I said, we're going to have something chiral, something kind of interesting. Let's use this guy right here. We're going to attack the carbon holding the bromine and get rid of the leaving group. And because this step of the reaction is SN2, we want to make sure that we're not using a tertiary alkyl halide. And also we want to remember to invert stereochemistry if we need to, if we have a chiral carbon. So initially what we get is going to look pretty big because we still have this big huge thing attached. We have created a bond between that nitrogen and, I'm going to number our carbons, the bond and the nitrogen and carbon number 2. So this is going to be our carbon 2. And we do want to be really careful about not screwing up the stereochemistry. So my plan is just to convert the wedge to the dash and the dash to the wedge and try to leave everything else pointing in the same general direction. So there's my carbon 1 and there's my carbon 3, 4, 5. And so this is the first product that we make in this reaction. And this is an amide. We've got our carbon-oxygen double bond adjacent to a nitrogen. It's actually a double amide. And that amide can undergo hydrolysis with the strong acid H3O+. So this is our step 3. This is going to be hydrolysis of the amide This is a reaction that you learned in chapter 21, and we're not going to draw the mechanism out for this because it's really tedious and it's really boring. And it's an acid catalyzed mechanism, which is even more tedious and even more boring. The hydrolysis of an amide produces a carboxylic acid. You can look back in chapter 21 if you have forgotten that. It is breaking these bonds that I'm squiggling right now. So it's breaking those bonds right there. So our other product is going to be our amine. And notice that nothing has happened to the chiral carbon in terms of changing its stereochemistry. And that's because we didn't do any chemistry to that particular carbon. Nothing happened at carbon number 2. So this right here, this is the product of the reaction, just like that. However, if you were actually doing this in the lab, because you have this carboxylic acid that you just made, plus you probably have some unreacted acid left over, that acid is going to protonate the beautiful amine that you just made. And it is going to, so I'm gonna start by just drawing 2, 3, 4, 5, drawing my amine. So that acid is going to protonate the amine because the amine is a base, and that's not the product that you want, which is why in step 4 we have to bring hydroxide in and undo that unwanted protonation, and we just are recreating that amine. 1, 2, 3, 4, 5. So there is our product.